Hello, everybody. So last time we brought up the idea that all molecules have an associated electronic energy. Now, one of the questions is how likely is it going to be to find a system in a given configuration with a given set of electronic energies? So in order to try and determine this, what we're going to try and do is figure out how frequently would I expect a molecular system to occur in a given state. So these frequencies of occurrence have a special name in statistics. They're called statistical weights. So we're going to be looking at the statistical weight or configurational weight of a system. So in classic statistical descriptions, you can figure out the weight of a system simply by knowing how many particles you're examining and knowing how many particles are going to be present in any given one of the possible states. So again, in this case, n is going to be the total number of particles in any given configuration we're talking about. And so NO is going to be the number of particles in the ground state, N1 in the first excited state, N2 in the second excited state, so on and so forth. So this may seem a little bit odd of a way to kind of describe a system. So let's go ahead and give an example in a very kind of simplified perspective. So let's say I've got four molecules. Each one can be in a given electronic energy, either say a ground state or a first excited state. So if all four particles are going to be in the ground state, this means that there's only going to be one possible arrangement that gives me this result, because there's no essentially statistical variance. So while this may be a very favorable sort of structure in terms of energy, it might be very unfavorable in terms of um, statistical variance, because things like to essentially spread out. For example, if I then go to this state where I move one of my particles up to the first excited state, it now counts four times as much as this initial structure, because guess what? Each one of these different particles can take a turn being the excited particle. So while it's less energetically favorable, it's more statistically favorable. And being able to try and calculate these weights can be fairly important. And again, it is worth noting in this description, we're mostly focusing in on the idea that all of these states are energetically equivalent. So let's go ahead and take a quick practice and try and figure out how to describe um, the configurational weights of various potential ways to put four objects in three energy levels. So again, the simplest possibility is I put all four particles in the ground state. So in this case, I have four particles, so it's n factorial. And then all of them are in this ground state, so that's n factorial as well. And then the remaining states have no particles, so they each get a 0 factorial. Now, this is an important thing to kind of remember. It turns out 0 factorial is actually 1. Feels a little bit odd, but that's the way these things work. So in this case, it means we have a weight of 1. All four particles are in one state. There's only one possible way to construct this. Similarly, if I move one particle up to that first excited state, I've got four particles total, so 4 factorial, divided by 3 factorial, times 1 factorial, times 0 factorial. You crank the numbers, and what ends up happening is we're left with as 4. Because again, you can think of 4 factorial as 4 times 3 factorial. And then the 3 factorials cancel, and these two values have a value of 1. We can also go ahead and imagine exciting one particle up to the third energy level. And it turns out this is going to have the exact same configurational state as if it was being excited to the second level. So in this case, it still also has a weight of 1 or weight of 4. Now, a little bit more exotic option is I take my four particles, I put 2 in the ground state and 2 in the first excited state. And in this case, what we find is that all of the particles, I still have 4 factorial in the numerator, but now I've got 2 factorial times 2 factorial times 0. Now, if you end up crunching the math, This one gets a little bit fun as we now have a weight of 6. So what we're kind of seeing here is that even though this may look energetically very favorable, we're already starting to see the hints of where StatMech starts to lead us. Excited energy levels have a much more tend to have much higher weights, as there's more possible ways to arrange the system, as they can have as I can take turns of having particles in an excited state. So there's a lot more configurational weight to these excited energy levels. So unfortunately, when we try and describe this system, let's be honest, it works okay for relatively small systems. But even by the time you get up to, say, 10 atoms, I don't know about you, but I don't like doing a lot of 10 factorials divided by 5 factorials, 4 and 3, or 4 and 1. That just gets a little bit inconvenient. So one of the common ways to try and simplify a configurational state, uh, a configurational weight equation, is to make use of our good old friend natural logs. So this actually makes use of a well-known mathematical approximation called Stirling's approximation, which really uh, is a critical foundation for statistical mechanics. And it's based on this simple idea that natural log of a of the factorial of a number is going to be the same as n times the natural log of that number minus that number. So the proof of this essentially makes use of several power expansions and canceling terms, but for now you can try and take me at my word. Now, there's only one problem with trying to use Stirling's approximation. It requires rather large numbers of particles. So, from our senses, it's not too bad because we're dealing with molecular level systems. My n may be, say, 10 to the 23rd. I can deal with large n's. It's my bread and butter. So, in this sense, Stirling's approximation is very well suited for statistical mechanics. However, it does tend to mean if you are trying to model small systems with statistical mechanics, some of our approximations start breaking down a little bit because we're going to often rely on this approximation because it allows us to simplify our configurational weights from this ratio of factorials, which is rather inconvenient. Instead, by taking a natural log of our weight, this is again the natural log of that ratio of factorials. But now I can make use of several features in natural logs. First of which is I can split it up instead of being a ratio into essentially a sum, where it's the natural log of the total number of particles, factorial, minus essentially a sum of the factorial of the number of molecules in each of the given states that I'm working with. So you can then combine this to essentially give it as natural log of the factorial number of particles minus sum of the natural log of the particles in each state factorial. Now here's where Stirling's approximation comes in, because I'm able to get rid of that factorial by giving the number of particles times natural log number of particles minus n minus pretty much the sum of the same thing with regards to the number of particles in each of the given energy levels or energy states that I'm examining. Now, we get another fun little simplification for free because the sum of the number of particles is just going to be number of particles in each state is just going to be the number of particles. So it turns out these two n's will end up canceling out. And all I'm left with is this essentially sum of natural logs, where it's again the number of particles, natural log number of particles, minus this essentially sum of each particle of particles in each state. So this is going to become one of our foundational places we're going to start with to describe a lot of the configurations of systems. However, there is several things we're going to need to take into account, as we have several constraints applied to our system. We've already used one very important one, which is that all molecules are going to only be present in a single state. So if I sum up the number of particles in each state, this should give me the total number of particles. Now that's going to help apply some constraints on this critical sum term. There's also another very important one, which is the fact that I can't just evenly spread out my number of systems, uh, my particles into the number of systems, because to maximize my weight, because it turns out I have to account for energy. So that works perfectly if every state has the same energy. But unfortunately, we have to deal with each state may have a different energy. And if I essentially sum the energy times the number of particles with that energy, I should get out the total energy of the system. And furthermore, uh, we also are going to approximate that the total energy shouldn't change upon any movements of the system. So if I change the number of particles in any given state, again, this should end up, the sum of these changes should be zero, but also the sum of the energy times these changes should also end up being zero. So for example, if I have one particle that goes up in energy, another one would have to go down. If one particle goes way up in energy, another one would have to go way down, or several ones would have to go slightly down just to keep this energy balance. And so these constraints are going to really limit what are going to be the most common configurations. They're really going to dominate our system. So next time, we're going to focus in on trying to determine which configurations are really going to dominate our description of uh, our statistical system of molecules. Until then, take care.